They are these beings that came from off-world, so these are aliens. These are aliens. NASA, renowned for its groundbreaking discoveries, has recently revealed that this new planet is not only intriguing due to its size and location but also because it exhibits lights that appear to be artificial. Are we on the verge of uncovering secrets that could change our understanding of the universe? Could this discovery mean there is life on other planets? Join us as we explore NASA's intriguing findings and uncover the truth about these extraordinary lights. In 2007, NASA launched the Dawn spacecraft with a mission to explore some of the most intriguing objects in our solar system. Dawn was uniquely equipped with 3 ion engines, allowing it to undertake an unprecedented journey. Dawn's journey began with a 14-month survey of Vesta, the second-largest asteroid in the belt. During this time, Dawn sent back detailed images and data revealing Vesta's complex surface and diverse geological history. After completing its mission at Vesta, Dawn embarked on the second and perhaps most exciting part of its journey, a detailed study of the dwarf planet Ceres. Thanks to its ion engines, Dawn was able to leave Vesta's orbit and set course for Ceres, a feat that traditional chemical propulsion would have found challenging. These engines provided a continuous, gentle thrust, allowing Dawn to travel vast distances efficiently and enter into a stable orbit around Ceres. Ceres, discovered in 1801 by Italian astronomer Giuseppe Piazzi, is the largest object in the asteroid belt between Mars and Jupiter. For many years, it was considered the smallest dwarf planet in our solar system until its reclassification in 2006. With a diameter of about 950 kilometers, Ceres is the largest and most massive body in the asteroid belt and one of the most intriguing due to its unique characteristics. As Dawn approached Ceres, scientists eagerly awaited the first detailed images of this mysterious world. They found bright spots scattered across its surface, most notably in a large crater now known as a Cater crater. These bright spots sparked immediate interest and speculation within the scientific community. Before Dawn's mission, the best image we had of Ceres was a fuzzy, low-resolution picture taken by the Hubble Space Telescope. Scientists knew so little about this dwarf planet, and the prospect of finally getting a close-up view was thrilling. What secrets would Ceres reveal? What new discoveries awaited? The mission promised to enhance our understanding of the solar system's formation and the role of water in shaping planetary bodies. The bright spots on Ceres are unlike anything observed on other asteroids. They appear to be composed of highly reflective material, possibly salts left behind by sublimated water. This finding hinted at the possibility of cryovolcanism on Ceres, a process where volcanoes erupt with water or briny liquid instead of molten rock. But what exactly are these mysterious lights, and what do they reveal about the nature of Ceres? Could they be evidence of ongoing geological activity or something even more extraordinary? Ceres stands out from other celestial bodies in the asteroid belt because of its size, mass, unique composition and potential for water and ice. Unlike typical rocky asteroids, Ceres has a composition more akin to a comet, suggesting it holds more secrets about the early solar system than we ever imagined. After 2 years in transit, the Dawn spacecraft finally began its approach to Ceres in early 2015. This moment marked a significant milestone in the mission as Dawn prepared to deliver humanity's first close-up views of the largest object in the asteroid belt. As Dawn drew nearer, the images of Ceres grew increasingly detailed, offering glimpses of a world that had previously been shrouded in mystery. The first images revealed a surface dotted with craters, indicative of a long history of impacts. However, it wasn't just the craters that caught the attention of scientists and space enthusiasts alike. Among these features were mysterious bright spots that boldly stood out against the darker rocky terrain. As the images continued to improve in resolution, the scientific community buzzed with theories about the nature of these bright spots. Were they ice patches reflecting sunlight, or could they be something even more exotic? Speculation ranged from mineral deposits to potential signs of cryovolcanic activity. To everyone's surprise, closer inspection revealed that the brightest spot was not a single entity but rather a cluster of several distinct spots. This discovery only deepened the mystery. The hypothesis that these were deposits of salts left behind by sublimating water gained traction. This would suggest that Ceres had or still has some form of geological activity capable of bringing water or briny liquids to the surface, where they quickly evaporate, leaving bright reflective residues. These findings challenged existing notions about Ceres, painting a picture of a more dynamic and complex world than previously imagined. The presence of such features hinted at the possibility of subsurface water or briny pockets, which could have profound implications for our understanding of the potential for life in our solar system. But what makes Ceres different from other planets? Ceres is an intriguing world often described as an icy planet with a rocky yet porous surface. Unlike most asteroids in the belt, which are primarily composed of rocks and metals, Ceres stands out due to its unique composition. Its surface is a mix of water, ice, and hydrated minerals, including clays and carbonates, which give it a distinct, less dense structure compared to its neighbors. This composition suggests that Ceres has a significant amount of water. The surface layer is rocky but porous, with ice and other volatiles trapped within. This icy characteristic is more reminiscent of a comet than a typical asteroid, hinting at a history that might involve a mixture of rocky and icy materials. Digging deeper beneath its surface, Ceres reveals even more fascinating aspects of its makeup. The dwarf planet is believed to have a differentiated interior consisting of a muddy mantle and a core. The mantle is thought to be rich in water ice, accounting for approximately 50% of Ceres' total volume. This mantle, likely a mix of rock and brine, surrounds a core that could be composed of a denser material, possibly silicates. The presence of such a significant amount of water ice suggests that Ceres may have once harbored liquid water, especially if its core was heated by radioactive decay early in its history. This internal structure sets Ceres apart from its asteroid neighbors and also raises intriguing questions about its potential for geological activity and the role of water in its evolution. But that's not all. The discovery of ammonia clays on Ceres implies that the dwarf planet may have formed in a colder part of the solar system and migrated inward. The presence of ammonia can lower the freezing point of water, supporting the existence of subsurface brines. These insights into Ceres' composition and history not only enhance our understanding of this intriguing dwarf planet but also provide valuable clues about the processes that govern the formation and evolution of icy bodies throughout the solar system. Cryovolcanism is a fascinating and relatively rare phenomenon. Geological processes, particularly when compared to the more familiar volcanic activity we see on Earth, are quite different on Ceres. Unlike traditional volcanoes that erupt molten rock, cryovolcanoes, also known as ice volcanoes, erupt volatiles such as water, ammonia, or methane. These substances can exist as liquids or gases in the extreme cold environments where cryovolcanoes are found. On Ceres, the cryovolcano functions by allowing water packed with dissolved salts to reach the surface. When this salty water makes contact with the vacuum of space, it rapidly sublimates, transitioning directly from a solid or liquid state to gas. This process leaves behind bright reflective salt deposits, which form the mysterious bright spots observed on Ceres' surface. The most famous of these bright spots is located in a crater named Decatur, known as Spot 5. This area has garnered significant attention due to its high reflectivity and periodic hazes observed by the Dawn spacecraft. These hazes are believed to be caused by the sublimation of water, which suggests that cryovolcanic activity might still be ongoing or occurred relatively recently. In addition to Spot 5, Ceres hosts several other bright spots, each with its own unique characteristics. These spots are not limited to a single area but are scattered across the dwarf planet's surface, indicating that cryovolcanism may be a widespread phenomenon on Ceres. The presence of these bright spots highlights the dynamic nature of Ceres and raises important questions about the potential for life in our solar system. The dynamic and active nature of Ceres challenges previous assumptions that it was a geologically dead world. As the Dawn spacecraft provided more detailed images of Ceres, a wealth of surface features began to emerge. The surface of Ceres is dotted with a variety of craters, each telling a story of the dwarf planet's history. Some craters are relatively shallow and eroded, indicating an old surface that has been subject to numerous impacts over billions of years. Others are more well-preserved with sharp edges and deep basins, suggesting more recent impacts. Interestingly, the number of craters on Ceres is fewer than initially expected. This discrepancy hints at geological processes that might be renewing the surface and erasing evidence of older impacts. One theory is that Ceres' icy composition allows for a form of cryovolcanic resurfacing where subsurface materials periodically well up and cover old features. This ongoing geological activity suggests that Ceres is not a static world but one that has been and possibly still is, dynamically evolving. Further evidence of geological activity on Ceres comes from the observation of fractures, grooves and troughs crisscrossing its surface. These features indicate that the crust of Ceres has experienced significant stress and deformation. Some of the fractures appear relatively young, possibly only a few 100 million years old, suggesting that the crust is still active to some extent. Grooves and troughs on Ceres likely formed as the crust was stretched and pulled apart, while rows of mountains and compressional ridges indicate areas where the crust was pushed together. These contrasting features provide a clear record of the internal forces shaping Ceres. Understanding these stresses and their origins helps scientists piece together the geological history of Ceres, revealing a world where internal and external forces interplay to create a diverse and active landscape. The unique geological activity observed on Ceres, from its cryovolcanoes to its stress-induced fractures, highlights the dynamic nature of this distant dwarf planet. The complexity of this dwarf planet enhances our understanding of Ceres itself and offers valuable insights into the processes that might be occurring on other icy bodies in our solar system. But that's not the only interesting thing that can be found on the planet's surface. One of the most striking features on Ceres is Ahana Mons, a solitary mountain that rises about 4 kilometers above the surrounding terrain. This unique geological structure stands out due to its steep slopes and relatively smooth, bright surface. Unlike other mountainous features on Ceres, Ahana Mons is not associated with any impact basin or apparent tectonic activity, making its origin a subject of considerable interest and study. Scientists hypothesize that Ahana Mons may be a cryovolcano, a type of volcano that erupts volatiles such as water rather than molten rock. The smooth, bright surface of Ahana Mons suggests that it is relatively young, with an estimated age of just a few 100 million years. This youth implies that cryovolcanic activity could still be occurring on Ceres, reshaping its surface. One leading theory for the formation of Ahana Mons involves the propagation of seismic waves. These waves might have been generated by a massive impact on the opposite side of Ceres. When seismic waves travel through a planetary body, they can focus at a point directly opposite the impact site, known as the antipode. This focus can cause localized heating and fracturing of the crust, potentially leading to the eruption of subsurface materials. In the case of Ceres, such an event could have created the conditions necessary for cryovolcanic activity, resulting in the formation of Ahana Mons. This theory is supported by the fact that Ahana Mons is located almost directly opposite a large, ancient impact basin on Ceres, suggesting that the impact played a critical role in its formation. Ahana Mons thus provides valuable insights into the internal dynamics and geological history of Ceres, highlighting the complex interactions between impacts, seismic activity, and cryovolcanism. The Ahana Mons on Ceres is a unique cryovolcanic feature, but similar mountains can be found on other icy bodies in the solar system, showcasing diverse geological processes. For instance, Olympus Mons on Mars, the tallest volcano in the solar system, rises 22 kilometers above the surrounding plains and is a shield volcano formed by repeated lava flows. Although much larger, it shares some characteristics with Ahana Mons in terms of isolated formation and steep slopes. On Jupiter's moon Europa, there are also signs of cryovolcanism, with features such as Thera and Thrace Macula. These regions exhibit evidence of ice flows and potential cryovolcanic activity, suggesting that Europa, like Ceres, might have subsurface oceans that occasionally breach the surface. Another example is Enceladus, a moon of Saturn, which has ice geysers erupting from its south polar region, driven by subsurface water interacting with the moon's rocky core. Another fascinating aspect of Ceres is the presence of water ice within its polar craters. These craters, located near the poles, are in a state of perpetual darkness due to Ceres' minimal axial tilt of just 4 degrees. Certain regions within these craters never receive direct sunlight, creating cold traps where temperatures are low enough to preserve water ice for extended periods. The discovery of water ice in these dark craters is significant for several reasons. It provides direct evidence that water, a key ingredient for life as we know it, exists on Ceres. This ice could be remnants from the early solar system, offering a glimpse into the primordial conditions that existed when Ceres formed. The stable, cold environments within these craters make them ideal for the long-term preservation of ice, much like similar features found on our moon. On the moon, permanently shadowed craters near the poles also harbor water ice. These lunar ice deposits are considered valuable resources for future human exploration, providing potential sources of water for life support and fuel production. The presence of similar features on Ceres suggests that this dwarf planet could also serve as a crucial outpost for future missions, offering resources that could support extended stays or even permanent habitats. Comparing the polar ice deposits on Ceres and the moon underscores the universality of certain geological processes in our solar system. Despite their differences in size and composition, both bodies exhibit similar mechanisms for trapping and preserving water ice. These parallels enhance our understanding of how water and other volatiles are distributed and maintained across different planetary environments. The study of Ceres' unique features, from the towering Ahana Mons to the icy polar craters, continues to reveal the dynamic nature of this dwarf planet. Each discovery adds a piece to the puzzle of Ceres' geological history, enriching our broader understanding of the processes that shape planetary bodies throughout the solar system. As we piece together the geological history of Ceres, it's clear that these discoveries wouldn't have been possible without the groundbreaking efforts of the Dawn mission. The Dawn mission stands as a remarkable achievement in the history of space exploration. Launched in 2007, Dawn was the first spacecraft to orbit two extraterrestrial bodies, Vesta and Ceres, providing detailed surveys and a wealth of data that have significantly advanced our understanding of these celestial objects. Over its 14-month survey of Vesta, Dawn mapped its surface, revealing its complex geology, including massive mountains and deep craters. Upon reaching Ceres, Dawn's mission entered a new phase of discovery. The spacecraft spent years orbiting Ceres, capturing high-resolution images and gathering extensive data on its surface composition, internal structure, and mysterious bright spots. These detailed surveys have offered unprecedented insights into the geological activity and history of Ceres. Insights into Ceres' geological history and current activity confirm the presence of water ice and suggest ongoing cryovolcanic processes. In 2017, as Dawn's mission drew to a close, the spacecraft was placed into a stable orbit around Ceres, where it remains to this day. This final resting place serves as a lasting monument to the mission's success, ensuring that Dawn will continue to orbit the dwarf planet for many years, possibly centuries. This enduring legacy allows future missions and researchers to build on the data collected by Dawn, furthering our understanding of Ceres and the broader asteroid belt. The success of the Dawn mission has paved the way for future exploration using ion propulsion technology. Dawn's ion engine, which provided a gentle yet continuous thrust, allowed it to travel vast distances and perform complex maneuvers that would have been impossible with conventional chemical rockets. This technology's efficiency and versatility have demonstrated its potential for future deep space missions, enabling spacecraft to visit multiple targets and conduct long-duration studies. The efficiency of ion engines, as demonstrated by Dawn, has paved the way for their use in other missions, such as the European Space Agency's Bepi-Colombo mission to Mercury and NASA's DART mission to the Didymos asteroid system. What do these discoveries mean for the future? The discoveries made by Dawn have had a significant impact on asteroid research, highlighting the importance of these small bodies in understanding the history and evolution of our solar system. The detailed data on Ceres' surface composition, internal structure, and geological activity have provided valuable insights into the processes that shape planetary bodies. This knowledge is crucial for planning future missions, whether they involve further exploration of Ceres, visits to other asteroids, or even the potential mining of asteroid resources. Moreover, the information gathered by the Dawn spacecraft supports the broader goal of identifying and studying celestial bodies that could pose a threat to Earth. By understanding the characteristics and behaviors of asteroids and dwarf planets, scientists can better predict their trajectories and develop strategies for planetary defense. As we advance our knowledge of these celestial bodies for planetary defense, we also uncover exciting possibilities for astrobiology, such as the potential for microbial life on Ceres. The discovery of water ice and potential subsurface briny reservoirs on Ceres has significant implications for astrobiology. Water is a crucial ingredient for life as we know it, and its presence raises the possibility that Ceres could harbor microbial life. The combination of water, minerals, and potentially active geology creates a promising environment for the study of prebiotic chemistry and the potential for life in the early solar system. Comparing Ceres to other icy bodies such as Europa and Enceladus, where similar conditions have led to the hypothesis of subsurface oceans, reinforces the importance of studying these environments. Understanding the similarities and differences among these bodies can provide insights into the conditions necessary for life and guide future astrobiological missions. Future missions equipped with advanced instrumentation could search for biosignatures or signs of life on Ceres. Such missions might include landers or probes capable of drilling beneath the surface to directly sample the subsurface environment, providing critical data on the potential habitability of Ceres. The bright spots on Ceres, particularly those within a crater, have been a focal point of intrigue and study. Dawn's high-resolution images and spectrometric data have provided substantial evidence that these spots are composed primarily of sodium carbonate, a type of salt. This discovery indicates that liquid water once existed on or near Ceres' surface, allowing these salts to be deposited when the water sublimated. Sodium carbonate's presence is significant because it suggests hydrothermal activity. When water-rich and dissolved minerals seeps through the crust and reaches the surface, it can evaporate and leave behind bright salt deposits. This process mirrors what occurs in terrestrial hydrothermal systems, such as those found in areas like Mono Lake in California. The detection of ammonium chloride and other salts further supports the notion of a salty liquid interacting with the surface, pointing to a dynamic geological past. In addition to sodium carbonate, Dawn identified other minerals in the bright spots, including various types of hydrated salts. These minerals are vital indicators of the past presence of liquid water, potentially sourced from Ceres' interior. The data suggests that cryovolcanic activity may have brought this water to the surface, where it then evaporated, leaving behind the highly reflective salt deposits. The bright spots periodic hazes, observed by Dawn, add another layer of complexity. These hazes are believed to be caused by water vapor sublimating from the surface, implying that subsurface briny reservoirs might still exist. This ongoing sublimation process highlights Ceres as an active body with a potentially volatile rich subsurface environment. Despite the wealth of data collected by Dawn, many questions about Ceres and its bright spots still need to be answered. One of the primary mysteries is the exact nature and extent of the subsurface water reservoirs. While the presence of salts indicates past or present water, the mechanisms driving the water's movement and its current state still need to be fully understood. Are they large underground oceans, or are the water sources more sporadic and isolated? Another area of active research involves the potential for cryovolcanism. While evidence points to past cryovolcanic activity, determining whether this process is still occurring requires further investigation. Understanding the triggers for such activity, whether they are internal heat sources or external impacts, is crucial for comprehending Ceres' geological dynamics. Additionally, the variations in the composition and distribution of the bright spots across Ceres' surface raise questions about the dwarf planet's geological history. Why are some regions more active than others? What historical events shape these patterns? These questions drive the need for continued exploration and data analysis. Future missions to Ceres could provide more definitive answers. Technologies capable of probing beneath the surface could reveal the extent and properties of the suspected briny reservoirs. Instruments designed to detect and analyze trace gases could confirm ongoing sublimation processes and provide insights into the current state of cryovolcanism. Collaboration among international space agencies such as NASA, ESA, and others could enhance the scope and success of future missions. Sharing data, technology, and expertise can lead to more efficient and successful exploration efforts, pushing the boundaries of our knowledge about Ceres and other celestial bodies. One of the most intriguing prospects raised by the Dawn mission's findings is the potential existence of subsurface oceans on Ceres. The discovery of significant amounts of water ice, particularly in permanently shadowed craters at the poles, suggests that liquid water could exist beneath the surface. This possibility opens up exciting avenues for further exploration. Future missions to Ceres could employ radar systems capable of penetrating the surface to search for liquid water reservoirs. Similar technology has been used on missions to Mars and Europa, where it has helped identify subsurface ice and potential water pockets. By mapping the distribution and depth of water ice on Ceres, scientists could gain a better understanding of the dwarf planet's internal structure and the dynamics of its volcanic activity. The presence of liquid water is a critical factor in the search for life beyond Earth. If subsurface oceans exist on Ceres, they could provide a stable environment for microbial life. The combination of water, salts, and possibly organic molecules could create conditions conducive to life, similar to those hypothesized for Europa and Enceladus. Understanding the potential habitability of Ceres involves studying its thermal history and the sources of heat that could maintain liquid water. Radioactive decay within the core and tidal interactions with other bodies in the asteroid belt might generate enough heat to sustain subsurface oceans. Investigating these heat sources and their effects on Ceres geology could reveal whether the necessary conditions for life have been present over extended periods. Thank you for watching another episode. While we still have you, click on any of the videos on your screen for the latest in space news.